Hi, I'm Norman Wildberger. Today we're going to have a look at a very important historical application of mathematics to understanding how to move around on a sphere and make some calculations involving triangulation. So we're going to have a look at the classical situation where we have a look at some points on planet Earth, 3 points on planet Earth, and try to figure out how to get from one place to another. We'll look at it from the classical point of view and also from the point of view of rational spherical trigonometry, and we'll see the vast superiority of thinking about things rationally. Okay, so to orient ourselves, we have to talk a little bit about the standard way of positioning places on planet Earth. So planet Earth is roughly a sphere. The radius is about 6,371 kilometers. If you want the radius in miles, you would divide by 1.6. Here is our sphere with the equator there. And so the sphere is tilted towards us, so the equator is sort of has this elliptic form, so the North Pole is visible up top there somewhere. And through the North Pole and the South Pole there are these great circles, lines of longitude. The line through Greenwich, England is the 0-degree line of longitude. And then every 10 degrees or so we can mark off another line. So we measure longitude in this direction, say by 10-degree intervals or whatever, going all the way around to 180. That's sort of in the east direction. And we can also measure in this direction here, going west up to also 180 degrees. Then in addition, to tell us how far north or south we are, we look at these other kinds of circles, meridian circles, which are not great circles, but sort of circles that you get when you slice the sphere with lines or planes parallel to the equator. So this would be 0 degrees latitude, and then if we go up a little bit, 20 degrees, 40 degrees, all the way up to 90 degrees. So this is in the northern hemisphere, everything is registered with the north, and correspondingly in the southern hemisphere we have lines 20 degrees south, 40 degrees south, all the way down to 90 degrees south. Okay, so to understand these two pictures, it's maybe convenient to have another look at the sphere from two different points of view. Here is a top view where we're looking straight down on the North Pole. The equator then would be just the rim of the circle. And these great circles that we're seeing here in this sort of elliptical shape would all be represented by straight lines. And this is supposed to be so the view from the North Pole. So there's Greenland and North America and Russia, Asia, Europe over here, Africa. There's Greenwich, England. So this line here would be the line of 0 degrees longitude. And the other lines of longitude are just obtained by going cyclically around. So from 0 up to 90 degrees, and then all the way up to 170, and then to 180. Or going west, 10 degrees west, 20 degrees west, up to 90 degrees west, up to 170 degrees west, and so on. So that's sort of the story for longitude. And the story for latitude we could visualize by looking at it from a side-on point of view, where the North Pole is right at the top, the South Pole is right at the bottom, and then the equator will be right across the middle. So we're looking at a side-on sort of slice through the Earth this way. Then these meridian circles are obtained by slicing the sphere with these planes parallel to the horizontal. This would be 0 degrees, that's the equator, and then something like 10 degrees, 20 degrees, 30 degrees, all the way up to 90 degrees at the North Pole, all in the northerly direction, 10 degrees, 20 degrees, 30 degrees, all the way down to 90 degrees in the South Pole. Okay, so this is the way we traditionally represent positions using very much an angular measurement system. And let's say a few words about that. So the role of angles here is twofold. There's an angle going around in the longitudinal direction, and there's also an angle being used in the latitudinal direction. This angle that's in the latitudinal direction is really an angle subtended from the center of the Earth. So when we're going up to 20 degrees latitude. What it means is that if we join our point to the center of the Earth, then this angle here subtended is 20 degrees. That's why it goes from 0 all the way up to 90. Now the role of these two angles is quite different. The role of the longitudinal angle is quite natural from an astronomical point of view, because after all, the Earth is in space spinning around like this once every 24 hours. And it's doing so uniformly. So if you're an astronomer and you're watching the night sky outside, you're going to have to take into consideration the fact that the Earth is rotating at a uniform rate. So the angular aspect in this longitudinal direction is a natural aspect to the story from an astronomical point of view. However, the latitudinal angle is not at all so natural. And there's a sense in which that's just a mimicry of the longitudinal angle. We just introduce it because we've already got one angle, so why not introduce a second one? But it's also important to say that if we're just interested in the sphere itself and not particularly interested in its rotational aspect, then it may very well be that these angular coordinates are not the optimal ones, and that the mathematics that we currently have to make calculations in this angular framework may not actually be the best framework. That's exactly the case. So it turns out that the rational framework, where we think in terms of spreads or projective quadrants instead, is much better for a lot of different calculations. So here are some places with corresponding coordinates. And it's usual to express the latitude angle first and then the longitude. So Greenwich, England, which has a historically sort of primary role in this subject because it, by definition, is the place where the line of longitude 0 goes through. That has coordinates 51.5 degrees north, 0 degrees east, or 0 degrees west. Toronto is 43.7 degrees north and 79.4 degrees west. Sydney, down here, is 33.8 degrees south, so that's how far south you have to go. It's the angle subtended at the center of the sphere between the equator and Sydney, while it's 151.2 degrees east. So Greenwich is almost on the other side of the world. You have to go almost all the way around to get to Sydney. Moscow's at 55.7 degrees north, 37.6 degrees east. Lima in Peru, 12 degrees south, 77 degrees west. Johannesburg, 26.2 degrees south and 28 degrees east. And New Delhi, 28.6 degrees north, 77 degrees east. So I'd like to calculate something now. I'd like to calculate how far is it from Sydney to New Delhi, and what direction do we have to fly to get there. So here's Sydney, and here's India, New Delhi up there in the north. N represents the North Pole in this picture, and we're interested in flying from Sydney to New Delhi. And when we say fly, we mean that we're taking our 2 points, Sydney down here and Delhi up here, and we're connecting those 2 points with a great circle, the shortest path on the globe. Okay, we want to know what is that distance, and we also want to know what direction would a pilot have to fly in initially from, say, the bearing north in order to go towards Delhi. Okay. So it's a very important kind of computational question, which is going to involve some very important spherical trigonometry, very classical stuff. And really it's a question that has fascinated humankind for literally thousands of years. The reason why it's so important is not because actually people were so interested in the geometry of the Earth. What they were more interested in is the geometry of the night sky, or the celestial sphere. It was pretty obvious to ancient peoples that the stars that surround us in the night sky were on some kind of sphere, because as you watch during a night, you can visibly see this sphere of stars rotating above you at a very steady pace. Stars that are on this side, eventually go over on that side, so you can see the whole thing move. So it's really the geometry of this celestial sphere that's out there, on which the stars are somehow pinned, it appears, that's really the main object of interest in astronomy. Okay, and it's to study that sphere that people introduced spherical trigonometry, and that the formulas that we're going to be talking about today really come from. And it's very interesting that these spherical formulas were much more studied than the planar ones. So planar trigonometry came along considerably after spherical trigonometry, because people very much had this picture of trying to understand what happens when you move around on a sphere in mind. Okay, so let's solve this problem in a rather modern language using the current system of measuring angles in radians. So historically, people would have used degrees, and okay, so it's a little bit different, but the essence of what I'm going to be talking about is really contained in Arabic, Persian work about 1,000 years ago. So it was really essentially known for quite a while. So here is Sydney again. Here are the coordinates of Sydney, latitude and longitude, and here is Delhi again. And here's our little picture of Australia down here and India right here, and we're going from Sydney to Delhi, and there's the North Pole. So we have this triangle, the spherical triangle consisting of 3 points on our sphere. And let's represent the various quantities that are traditionally studied by, say, letters capital N, capital D, and capital S to denote the angles here. So capital N also refers to this angle here, capital D to this angle here, capital S to this angle here. And the little s and little d and little n represent the distances between the points, the sides of this spherical triangle. Okay, so what do we know? Well, the first thing that we can figure out is this angle here. Okay, so what do we know? Well, we know that here are the longitudes. Delhi's at 77 degrees east, and Sydney's at 151 degrees east. So there's the line through the North Pole and Greenwich, the line of 0 longitude. Then we have to go an angle of 77 degrees to get to the line through Delhi. We have to go an angle of 151.2 degrees to get to the line through Sydney. So the angle between those two lines is going to be the difference between these two angles. So that's 74.2 degrees. That's the angle between these two great circle lines emanating from the North Pole, one going through Delhi and the other one going through Sydney. That's one ingredient in our spherical triangle. What about this S here? Well, in classical spherical trigonometry, the S is measured, it's a distance, but it's measured in terms of the angle subtended at the center of the sphere. Now what we do know is that the angle subtended at the center of the sphere by Delhi and the equator, that is the latitude of Delhi, which is 28.6. So this angle here is 28.6, that angle right there. Now since from the equator to the North Pole is a total angle of 90, from Delhi to the North Pole will then be 90 minus 28.6, or 61.4 degrees. And that's how we measure that side in classical spherical trigonometry, kind of assuming the sphere has a radius of 1, if you like, currently. So that's S, it's equal to 61.4 degrees. And similarly for Sydney, Sydney is at 33.8 degrees south. That means that the angle from here to here, subtended at the center, is 33.8 degrees. And to go from the Sydney then to the North Pole is another 90 degrees added on to that. So the total angle there between Sydney and the North Pole is 90 plus 33.8, which is 123.8 degrees. So that's going to be that side of our spherical triangle. So very good, we have 3 pieces of information about this triangle. So we have enough to, in principle, apply some trigonometry and try to figure out the other pieces of information. But one thing that we want to do first is to convert from the ancient Babylonian system of angles to the more modern system of radians. Let me remind you that the basic conversion there is that 180 degrees is pi radians. So n, for example, which is 74 degrees, to convert it into radians, we'll multiply by pi and divide by 180, giving us 1.3 radians. This s, which was 61.4 degrees, that converts to 1.07 radians, and 123.8 degrees converts to 2.16 radians. So everything is a radian, an angle measured in radians. Good. So let's represent our spherical triangle with this diagram right here. Sort of dispense with the sphere. We know we're on a sphere. We'll have slightly curved sides to kind of remind us that we're talking about spherical trigonometry. We've decided that this angle here is 1.3 radians. This side is 1.07 radians. This side is 2.16 radians. This is an angle which is just the usual angle between that side and that side. These sides as angles are a little bit more subtle. They're the angles subtended from this center of the sphere that we actually can't see it right now. And the other quantities, well, there's other angles at the other 2 vertices. Let's call them capital D and capital S. And there's also this side here, which we'll call little n, because it's opposite capital N. Right. So, key formula in the subject, the cosine law, the spherical cosine law, which says that cosine of n equals cosine of 1.07 times cosine of 2.16 plus sine of 1.07 times sine of 2.16 times cosine of this angle, 1.30. Here it is there. All right, so we can calculate cosines because cosine is given by a power series. Cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial and so on. There's a well-known power series that undergraduates learn. And your calculator uses something like that to spit out a value or an approximate value for cosine. To actually use that power series, well, you could do it. You could use the first 10 terms and you would get a reasonable approximation. So one way or the other, we can get an approximate value for cosine 1.07, approximately 0.480124. It's definitely not the real value, but it doesn't really matter because we're just talking about measurements anyway. None of the values that we have here are exactly correct. But in principle, it's still important to observe that even if we did know these numbers exactly correctly, we still wouldn't have exact answers at this point. So going from here to here, we go from pure information to approximate information, even in the best of situations. The cosine of 2.16 is minus 0.55, etc. Sine of 1.07, 0.877. Sine of 2.16 is 0.8313. Cosine of 1.3, 0.267. So our calculator does all that work, and then it makes this calculation, and you get approximately minus 0.071720, etc. So that's the cosine of n, and now we have to invert that. We have to extract n from that. And there's another series again that we talked about in our last video. Or you can just press the appropriate button on the calculator and you get that n is arc cosine of this number, which is roughly 1.642, etc. Okay, so now of course the Persian mathematicians did not have calculators, but they had tables. So they had tables of values for sines and cosines. And you could use that table to sort of go backwards by interpolating to find angles if you knew the values of sines. So these tables were crucially important in these kinds of calculations, and people spent a lot of time and effort making good tables. It's not so easy to make good tables for these various functions. So after we've gotten 1.642, we have this thing as an angle. So we can actually calculate the distance. Because if we have a sphere here, okay, then the angle pi would be, say, from this point on the equator to the opposite point on the equator. And we happen to know about the geometry of the Earth that the circumference divided by 2 is almost exactly 20,000 kilometers. In fact, when the French famously set up the metrical system after the French Revolution, they introduced the meter in pretty well exactly this way. They said that we'll take the North Pole and we'll go through Paris to the equator, and we'll say that that distance is 10,000 meters. So the meter was introduced as an object relating to the size of the Earth. And so it's not a surprise that we get almost exactly 20,000 kilometers for this half of a circumference. All right, so if pi radians translates to 20,000 kilometers, then 1.64 radians is going to translate to 1.64 times 20,000 over pi, which turns out to be 10,456 kilometers. If you divide by 1.6, the corresponding amount in miles is 6,510 miles. And on the internet, I just checked that the actual distance is 10,426 kilometers. So we've done pretty well, considering that we haven't been too fussy about accuracy, and we just started out with rough coordinates. All right, so very powerful computation that we've just done here. Okay. We have calculated from just knowing the relative positions of these 2 points on the Earth in terms of this spherical coordinate system. We've calculated the distance between them. So it's a really very, very vital kind of technology for astronomy. All right, so very good. We can go a little bit further though. Now that we have this third side, 1.64, also in radians, we can now find these 2 angles here. And for that we use the sine law, which says that the sine of this angle divided by the sine of the opposite side is the same as the sine of this angle divided by the sine of the opposite side is the same as the sine of this angle divided by the sine of the opposite side. Unfortunately, we have both of these things in hand, and so we can pretty easily compute that sine of d is, once we take this thing up there and multiply it by those things, it's 0.803, etc. And sine of s is 0.847, etc. Okay, and then we can look up our tables, or if we have a calculator, look at the arcsine function and invert these values to find that the corresponding angles d and s are 0.933 and 1.01. Everything in radians. So the angle d here we've said is 0.93, let's say, and the angle here is 1.01. And if we wanted it in degrees, well, then we would convert the radians to degrees. We do that by multiplying by 180 and dividing by pi. And there we would get 53.4 degrees. And s would get 57.9 degrees. But it's important to realize here that knowing the sine of an angle doesn't entirely tell you what the angle is. Because, for example, if you have this angle here, and you have pi minus theta, that angle there, both of those angles have the same sine. So just because you know the sine of an angle doesn't quite mean that you know the angle. You still have to sort of figure out, depending on the actual geometry of things, whether you're talking about theta or pi minus theta. And in this case, if one looks at the geometry of things, in fact, if one just looks at the story here, we're going from, let's see if I can show you here, I don't know if you can see that, but we're going from Sydney, which is down here, to New Delhi, which is up here, and we're referring to the North Pole. So there's the line of the North Pole coming down. We're going from here to here, meeting that line there. It's going to be obviously more than 90 degrees. So in fact, we need to replace this thing with 180 minus that angle. So the angle is really 126.6 degrees. So I probably should really put here, this angle is not this thing here, but pi minus the 0.93 would be the actual correct value there. Great, so we've solved the entire situation. We know what kind of an angle our pilot needs to take. There's true north from Sydney, so our pilot has to take bearing of north and has to veer off at an angle of 1.01 radians and then go in that direction for about 10,000 kilometers, and he will get to New Delhi. Now we want to have a look at this same problem from a rational point of view. So these days, of course, we don't use sine and cosine tables. We have calculators, we have computers that will calculate these things very quickly for us. Still, it's important for us to find a technology that's efficient, because for many, say, complicated graphical problems, like let's say you're making a video or some 3D rendering that's going very fast and things are moving around quickly, you have to make a lot of computations. And so even though one computation you could do very quickly, if you have to make billions of computations, you want the computations to be still pretty efficient. So what happens if we change our point of view and adopt this rational trigonometry orientation? So we're going to have to change the input as well, and then we'll see how the calculation proceeds. And we'll see that the calculation proceeds much smoother. So one of the first things we have to do is to convert our original data from angles to spreads, or in our language, projective quadrances. And here's the basic story here. Here's a unit circle. Here's a traditional angle from here to here, say theta. Then that angle corresponds to a corresponding spread, S. And how do you get S from theta? Well, here's a connection. S is equal to sine squared theta. Now, this is not the way we define the spread, because in fact the spread is a purely algebraic quantity that doesn't depend on the essentially transcendental nature of angles. Just to define angles really requires calculus. To define the spreads just requires some basic geometry or maybe a little bit of linear algebra. But nevertheless, this is the relationship that allows us to go from one to the other reasonably smoothly. So for example, here are the coordinates of Sydney. We'll look at them again. Here are the angle coordinates. First we'll convert them into radians. Okay, so here are the radian values instead of the angle values. And then to get the corresponding spreads, we just take the square of the sine of the angle. We compute the sine of an angle and square that. Okay, so 33.8 degrees turns out to be a spread of 0.31. 151 degrees turns out to be a spread of 0.231. So let me remind you again that if the horizontal is our reference frame, okay, here's how spreads work. Okay, spreads go from 0 to 1. And then if you keep going, they go back from 1 to 0. So it's 0, 0.1, 0.2, 0.3, but when you get to 45 degrees, that's a spread of a half. Okay, and then it goes from half all the way up to 1. And then if you keep going, it goes back to a half again, then back to 0. And a spread of 30 degrees is exactly a quarter. A spread of 60 degrees is exactly 3/4. So the kind of crucial angles correlate to the spreads 0, 1/4, 1/2, 3/4, 1. And then it goes 3/4, 1/2, 1/4, 0 again. Okay, what about Delhi's position? 28.6 degrees and 77 degrees, they translate to radians, 0.5 and 1.34, corresponding spreads, take these values, take the square of the sine, you get 0.229 and 0.948. Okay, so how should we think about that in terms of where these things are? So here's again our top view of the world. And here is North Pole, 0 line Greenwich. That's supposed to be Africa. There's Greenland, North America. There's Asia. There's India there. And so the line through Delhi, that spread from 0 Greenwich to the line through Delhi is a spread of 0.948. Means it's almost, it's getting close to 90 degrees, but not that close yet. It's not a linear scale, okay? It sort of has a quadratic aspect, which is especially prevalent near 0 and 1. And Sydney, well, you have to go over a little bit further to Sydney, and you actually have to go around to the other side, but in any case, the direction from the North Pole, the spread between this line and this line, spreads are only defined in terms of lines really, is going to be 0.231. There's the 0.231. And in terms of the latitudes, here's the sort of side-on view with the North Pole right at the top, South Pole right there, equator along here. There's India, roughly. And so we're looking side-on. This 0.310, that's the latitude spread for Sydney. Here's Sydney down here. This spread from here to here will be 0.310. Okay, so what do we actually need to do? Well, we really have a triangle here. So the triangle is still the North Pole, Delhi, and Sydney. We want to analyze that triangle. In order to get this value here, we're going to find this certain spread here. Okay, there's sort of a spread here. Let's call it spread at the North Pole. We're going to have to find that. And also I'll remind you that if you have a 90 degrees or perpendicularity there, if this is a spread of s, then this will be a spread of 1 minus s. So for example, if you want to know what this spread is, it will be 1 minus 0.229. If you want to know what this spread is, it will be 1 minus 0.310. So we have enough information to recast the original information about positions of latitude and longitude of Delhi and Sydney in terms of spreads on our spherical triangle. Spreads and quadrances of our spherical triangle. Okay, so let's try to put together the rational form for this triangle. There's the North Pole, there's Delhi, there's Sydney. What about the spread here? Well, we've seen that this spread is 0.95. That's the longitudinal spread made by Delhi. And the longitudinal spread for Sydney is 0.23. So if n is the spread at point n in this triangle, so then 0.95, 0.23, and n are 3 spreads formed by 3 concurrent lines. To find n, we have to use the triple spread formula. It's the relation between 3 concurrent spreads. So 0.95 plus 0.23 minus n all squared equals 4 times 0.95 times 0.23 times 1 minus n. That's kind of an efficient way of writing the triple spread formula. Also sometimes called the projective triple quad formula. This is a quadratic equation. So we have to solve this quadratic equation, and that will prominently figure taking an approximate square root. Everything's only approximate here, so we just have to get an approximate square root to find the two values. N is, say, 0.93 or n is 0.56. Okay, now we have to look at the situation and decide which one of these is the relevant one. So we had a situation like this when we were looking at it from the North Pole. Here's the North Pole. We had 0.95 here, 0.23, and we're interested in this spread here. So a little bit of thinking shows that the n has to be the 0.93 here. The other value would be when you take the 0.95 and you subtract sort of this same thing from the same thing, you get a much smaller spread. So you have to look at the geometry one way or the other and maybe apply some reasoning having to do with the configuration to determine which of the solutions you're going to use. So now we have the situation where we know this spread here is 0.93. We've converted these two by subtracting them from 1. So we have 1 minus 0.23 and 1 minus 0.31. Those are then the projective quadrances from the North Pole to Delhi and to Sydney. So those are now our 3 pieces of information from this rational point of view. So at this point now we've converted the original data having to do with angles, longitude, and latitude to values of spreads and quadrances. So in our spherical triangle language, we have a spread of 0.93 here, 1 quadrant of 0.77, another quadrant of 0.69. There's still an unknown quadrants on this side and 2 unknown spreads at these 2 vertices here. And so now we want to see, how do we solve this with rational elliptic geometry? Okay, so we're going to use the analog of the cosine law, which is the more fundamental cross law, a really powerful law. It's what's really going on here. Okay, the cosine law is a shadow of this law. So this one is telling us that there's a relationship between this spread, S sub n, and the 3 quadrances 0.77, 0.69, and Q sub n. So if we call this quadrants Q sub S, this quadrants Q sub D, then the abstract formula is that Sn times Qs, Qd minus Qs minus Qd minus Qn plus 2 all squared is 4 times 1 minus Qd, 1 minus Qs, 1 minus Qn. Okay, we have these 3 values. We can plug things in. The thing that we don't know is Q sub n, so there's going to be a Q sub n appearing there. There's Sn, there's Qs, Qd, Qs, Qd minus Qn plus 2 all squared is 4 times 1 minus Qd, 1 minus Qs, and the unknown 1 minus Qn. So Qn appears there, and there is a quadratic equation then, because that term's squared. So we just calculate what's inside, expand it out. We do this with a pen and paper. We get the equation Qn squared minus 1.783 Qn plus 0.784 equals 0. We get approximately like this. I've left off some extra digits. So we have to apply the quadratic formula, and we have to take an approximate square root, and we get 2 solutions, 0.787 or 0.995. We have to look at these 2 solutions and decide which one is the relevant one. It turns out this one's the relevant one. And we can check that the actual value that we got earlier using the classical derivation, which was a radian measure of 1.64, has the property that if you take the sine squared of 1.64, you do indeed get 0.995. So what we're getting here is just exactly the rational analog of the computation that we made earlier with the classical cosine law. And what about these other spreads, S sub D and S sub S? Well, we're going to use the spread law, which is that S sub D over this quadrant equals S sub S over the opposite quadrants equals this spread over the opposite quadrants. Well, that's immediate. We're just doing a bit of multiplication and division. We get S sub D equals 0.64 and S sub S equals 0.72. So we've immediately obtained the spreads there and there. And we can check that yes, indeed, 0.64 is, up to 2 decimal places, sine squared of 126.6 degrees that we got classically. And that 0.72 is indeed sine squared of 57.9 degrees that we got classically. And let me iterate again. Okay, this has been, in principle, a pen and paper calculation. I've actually used the computer because I've just been a little bit lazy, but I could easily do this by hand. I don't need any lookup tables. I don't need to have any values or power series for cosines and sines and arc cosines and arc sines. The only computation that I need to make, which is somewhat involved, is taking a square root. And of course, I'm not really taking a square root, I'm just taking an approximate square root. I'm taking the ancient Babylonian or Hindu algorithm and running it to a certain extent till I have 2 or 3 decimal places, however many I want, and then I stop, and then I proceed. So I think it's fair to say that this is really, an order of magnitude superior, more efficient than the other one, than the classical result. And you can check this for yourself. So it's a great exercise now, because we've covered quite a lot of material here, is to really work this out by having a look at some examples yourself. Take 2 of your favorite cities on planet Earth. Look up their latitudes and longitudes and sit down and say, I'm going to figure out how far these things are away from each other and what angle or what spread a pilot needs to orient himself so that they can get from A to B. And you can follow the argument. You can try it with the classical method, and you can try it with the rational method. In fact, it's really good if you try both. You will get a very solid appreciation for the power of thinking rationally. And if you're a programmer and you have to work with three-dimensional things which are moving around a lot, and you have to make a lot of calculations involving angles and such, this is a strong indication that it's probably advantageous for you to shift your orientation. Okay? Let go of the angles, adopt the point of view of rational spherical trigonometry. In our next video, we're going to go back to the ancient Greeks to a certain extent and look at a regular tetrahedron. We're on our way to addressing the beautiful geometry of the Platonic solids. So it turns out that the framework that we have now, the tools at our disposal, allow us to get a whole range of new and beautiful insights into the geometry of three-dimensional space, but in particular to the Platonic solids that were a main object of interest to Euclid and the other ancient Greeks. So I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.